In crystals, the repeating patterns are represented by points in the space. For example, here are 3 different structures with different repeating patterns. If each repeating pattern is represented by a point at its center, the 3 crystals have the same structure of points. The structure of those points defines the crystal structure. A Bravais lattice is a repeating arrangement of points. For simplicity, we just call it lattice. Pay attention, lattice is a pure mathematical concept. A lattice is completely determined by its primitive vectors, which are vectors in Euclidean space. In an n-dimensional space, the primitive vectors are denoted as a1 to an, or a, b, c, etc. Any point of the lattice is determined by a set of integers, u1 to un. The vector of the position of the point is a linear combination of the primitive vectors. For example, the primitive vectors in this 2-dimensional space are a and b. Suppose the origin is the red point. The vector for the green point is 2a plus 3b. The vector for the blue point is minus b. The unit cell is the repeating unit in a crystal, which cannot be further divided into smaller repeating units. In the following example, all the quadrilaterals are repeating units, but only 2 of them are unit cells. You can check that there is no way to divide them into smaller repeating units. It is proved that the opposite sides or planes of a unit cell are parallel to each other. So, unit cells are parallelograms in 2-dimensional space and the parallelepipeds in 3-dimensional space. The lengths of the edges of the unit cell and the angles between them are the lattice parameters. The lattice structure is fully determined by the lattice parameters. Here, we use lattices in 2-dimensional space as examples. In 2-dimensional space, the lattice parameters are length a, b and the angle between them, theta. According to the difference in symmetry, there are 4 types of lattices in 2-dimensional space. For example, if a is not equal to b, and theta is not equal to 30, 90, or 120 degrees, the lattice structure is monoclinic. In orthorhombic, hexagonal, and tetragonal lattices, there are 2 types of unit cells. The smallest unit cell is a primitive cell. The primitive cells are shown in red in the examples. Here is a real 2-dimensional material, graphene. In this structure, each ball is a carbon atom. Each stick is a carbon-carbon bond. The repeating pattern can be found like this. It is the primitive cell of graphene. The lattice of graphene is shown on the right. It is obviously a hexagonal structure. In 3-dimensional space, there are totally 14 different lattices, according to their different symmetries. They are categorized into 7 lattice systems according to their shapes of the unit cells. When discussing the lattices of crystals, the lattice system is also called the crystal system. In general chemistry, we will use the simplest crystal system, that is, the cubic crystal system, to study the crystals. The unit cell of a crystal of cubic crystal system is a cube. There are 3 lattices in this system. Since the unit cell is cubic, the lengths of 3 edges are identical, and the angles between them are all 90 degrees. The simplest cubic lattice is the primitive cubic lattice. It has 8 points on 8 vertexes of the unit cell. Pay attention, each point is shared by 8 unit cells. Therefore, there is 1 point per unit cell. The body-centered cubic lattice is abbreviated to BCC lattice. Besides 8 points on 8 vertexes, there is 1 more point at the center. The central point is owned by the unit cell exclusively. Thus, each unit cell has 2 points. Pay attention, even though the points on the vertexes and at the center seem to be different, they are actually equivalent. The face-centered cubic lattice is abbreviated to FCC lattice. In addition to the points on the vertexes, there are 6 points at the centers of the 6 faces. Each point on the face is shared by 2 unit cells. So, there are totally 4 points per unit cell in FCC lattice. The points on the vertexes and on the faces are equivalent. The coordination number is the number of closest points to 1 point in the lattice. For example, the coordination number of primitive cubic lattice is 6. Each point is closest to the points above, below, to the left, right, front, and back of it. The coordination number of BCC lattice is 8. The point at the body center is closest to 8 points at the vertexes. The coordination number of FCC lattice is 12. The point at the face center is closest to the points at the vertexes. Each face has 4 vertexes. Each point is shared by 3 faces. So, there are 12 closest points. Here, I show you the unit cells of some crystals. Please practice by yourself to calculate the number of each type of atom in the unit cell and its coordination number. Let me show you an example. In calcium fluoride, the white balls form FCC structure. So, there are 4 white balls per unit cell. On the other hand, all the yellow balls are inside the unit cell. There are 8 yellow balls per unit cell. Thus, the ratio between the white and yellow balls is 1:2. Therefore, the white ball is calcium. The yellow ball is fluorine. A fluorine atom is surrounded by 4 calcium atoms. Its coordination number is 4. A calcium atom is surrounded by 8 fluorine atoms. Its coordination number is 8. In crystals, the lattice points are usually the centers of the constituent particles. Here, we use pure metals as examples. In pure metals, the constitutional particles are identical ions. They can be regarded as identical balls. Each ball has a volume. The balls cannot fill the whole space. There must be interval between balls. The atomic packing factor is the fraction of volume occupied by the balls. To calculate APF, suppose the length of the edge of the unit cell is A. The volume of the unit cell is A cubic. The radius of the ball is calculated using geometry. Please pause the video here to check the process of calculation by yourself. After finding the radius, the volume of a ball is calculated. The volume occupied by the balls is the volume of one ball multiplied by the number of balls per unit cell. The APF is this volume occupied by the balls divided by the volume of the unit cell. The FCC lattice has a APF about 0.74. We will see that it is the highest possible APF for a single type of atom. There was a long-lasting question about how to pack as many as possible identical balls in a fixed space. Now let's try to do it. The packing is done layer by layer. It is not difficult to find that, in 2-dimensional space, the best packing is the hexagonal packing. In the 2-dimensional hexagonal packing of identical balls, there is a void in the center of 3 balls. Meanwhile, each ball is surrounded by 6 voids. So, the number of voids is twice the number of balls. There are 2 groups of voids, denoted in blue and yellow respectively. Each group forms the same hexagonal structure as the balls. After packing the first layer, layer A, the second layer, layer B, is packed above layer A. To save space, the balls of layer B have to be right above the voids of layer A. Suppose the balls of layer B are right above the blue voids of layer A. Layer B also has 2 groups of voids. One group is right above the balls of layer A. The other group is right above the yellow voids of layer A. So, there are 2 choices when packing the third layer, layer C. Here we pack layer C in such a way that its balls are right above the voids of both layer A and layer B. Layer C has 2 groups of voids. One is right above the balls of layer B. The other is right above the balls of layer A. If the balls of the fourth layer are right above the balls of layer A, it is a duplication of layer A. Similarly, the 5th layer is a duplication of layer B. The 6th layer is a duplication of layer C. And the 7th layer is a duplication of layer A again. The packing can be continued by repeating layers ABC, ABC, and so on. It is called ABC stacking. It is a so-called closed packing because it has the highest possible packing factor. Please have a close look at the ABC stacking. It is exactly the same as the FCC packing. Another way to pack the third layer is to put its balls right above the balls of layer A. It is a duplication of layer A. Similarly, the 4th layer is a duplication of layer B. And the 5th layer is a duplication of layer A again. The packing can be continued by repeating layers AB, 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 and so on. It is called AB stacking. AB stacking is also known as hexagonal closed packing. It is because the lattice of AB stacking is hexagonal and its APF is the highest, the same as the ABC packing. In AB stacking, each ball is closest to 6 other balls in the same layer and the other 6 balls from the layers above and below it. So, the coordination number of AB stacking is 12. Here, I show you a periodic table showing the structures of solids of elements. You can see that many metals have either FCC or HCP lattices. It is because the closed packing maximizes the coordination number. A higher coordination number means more bonding between atoms, and the system is more stable. However, there are also many metals with other lattices. The lattices also change with temperature and pressure. The reason is quite complicated. Generally speaking, in metals, covalent bonds, which are in certain directions, also contribute to the bondings in metals. A single crystal is a solid, in which the crystal lattice of the entire solid is continuous. For example, the microchips are made from single crystal silicon. A solid is polycrystalline if it has non-continuous crystal lattice. The continuous lattice parts in polycrystalline solids are crystallites. They are also called grains. For example, in polycrystalline silicon solar panel, the crystallites are quite visible with different reflections. The properties of crystals are anisotropic. For example, graphite is strong and conductive in the plane of the graphene, but is much weaker and less conductive in the direction perpendicular to it. Thus, to discuss the properties of crystals, we must identify the direction. Miller index is a notation of direction and lattice planes in crystallography. There are 3 integers in a Miller index, h, k, and l. Suppose a, b, and c are lattice parameters. The Miller index h, k, l represents the planes which intercept primitive vectors at points a n over h, b n over k, and c n over l. Here, n can be any integer. So, a set of h, k, l does not represent a single plane, but infinity number of planes. Those planes are parallel to each other and equally spaced. The Miller index can also be used to represent the direction normal to the planes. Here, I show you the planes and their Miller indices in cubic unit cells. Pay attention, an index 0 means that the plane never intercepts the primitive vector, so the plane is parallel to it. For example, the 1, 0, 0 planes are parallel to A2 and A3. They intercept the primitive vectors A1 at 0, A1, 2A1 and so on, as well as -A1, -2A1 and so on. In Miller index, a negative sign is represented by a bar over the number. Please practice finding the other planes in the figures using the Miller indices by yourself. Let's use FCC crystal as an example. Imagine we slit the crystal through one of the planes. If the plane is 1, 0, 0, we should see a section like this. If the plane is 1, 1, 0, the section should be like this. If the plane is 1, 1, 1, the section should be like this. The formula for the distance between planes of cubic lattice system is shown below. The most widely used technique to study the crystal structures is X-ray diffraction. When X-ray illuminates a substance, it is scattered by its atoms. The scattering by a layer of atoms in a crystal is similar to the reflection by a mirror. Pay attention to the X-ray pathways 1, A, 1', and 2, C, 2'. At point 1 and 2, their phases are equal. Because the 2 pathways are scattered by neighboring layers of atoms, their optical path lengths are different. The difference is the length of B, C, D. It equals 2d sine theta. D is the distance between the layers. Theta is the angle between the incident X-ray and the layer. The scattered X-ray diffract with each other. For a diffraction enhancement, the difference in optical path length must be integer times of the wavelength. So, we have the Bragg's law. The intensity of the scattered X-ray is a function of theta. In experiment, theta is changed by rotating the X-ray source and detector. The angles of the peaks correspond to the distances between the lattice planes. Each crystal has a certain set of distances between its lattice planes, so the type of crystal can be identified from its XRD spectrum. Pay attention that the variable in XRD plot is the angle between the incident and scattered X-ray, that is 2 theta. Here, I show you an example of XRD of a mixture of silver and silver chloride. Both silver and silver chloride have cubic crystal system, so their XRD spectra have similar patterns. However, silver chloride has bigger unit cells, so the angles for the lattice planes are smaller than those of silver with the same Miller indices. The angle between the X-ray source and detector can be controlled in two directions. By doing this, we have the two-dimensional XRD. The structure of DNA was discovered by analyzing the two-dimensional XRD of it.